Okay, so what does this mean? Well, we're going to, last time I talked about Schrodinger specifically solving the puzzle of the hydrogen emission spectrum. So atomic spectroscopy, is this on timer? Okay. So atomic spectroscopy give you line spectra, and these line spectra were inexplicable. It showed that the electron had a particular energy that it could have and other energies it could not have. And this wasn't explainable with Newtonian physics. So de Broglie introduced the idea of standing waves, and then Schrodinger developed the math to solve that spectrum. So today we're going to look at that math. So all of this math is from Schrodinger's paper, not exactly from Schrodinger's paper, but it's the same kinds of equations that he solved. But we're not going to solve them today. It's going to take us a whole week. So next week we're going to solve each of these equations. Specifically in the lab, we're going to look at them in detail. And so I'm just laying out now the integrals that you need to do and the differential equations that you need to do. And then we'll use our first and second semester calculus next week in the lab for you to do a few of those for two reasons. One, I want you to refresh your skills in calculus. It was a prerequisite after all. I'd hate for you to have a prerequisite that you didn't use, right? It'll refresh your memory on that. Two, it'll show you how, at least for our particle in a box system, it's not that bad. You have like two integrals to do. You have one integral that's integration by parts, and so we'll dust that off and use it, okay? And then we do a second derivative, okay? So it's just not too bad. We're dealing with cosines and sines, and we have like a couple of trig substitutions. So that's it. That's really not like this enormous, when you think, oh gosh, calculus. Yeah, well, calculus was a whole semester of horror, okay? This is just a few problems. And with that, you can actually predict the spectrum. So let's kind of run this backwards. Instead of starting with the wave function, let's start with the spectrum, because that's what we would go into the lab and that's what we would get. So let's start with the data, and then we're going to drill down and tear apart the spectrum until we get to the wave function. Okay. So we're going to introduce these terms that I talked about last time, energy levels and spectral lines. And so this is important to get these concepts, and these words both begin with L. They both sound very similar, but they're very, very different. So energies are quantized. And so when light is emitted, an electron or nucleus or a molecule or an atom drops from a higher energy level to a lower energy level. So the levels are just like floors in a building. And a molecular system can be on a floor 1, floor 2, floor 3. Those are your energy levels. It's the transitions between the levels that we call spectral lines. Those show up in the spectrum. So we have these three spectral lines shown with these arrows. So notice how the energy levels are fixed on this y-axis. The y-axis is energy. And those levels are the solutions to the Schrodinger equation. And then it's transitions, it's jumps up or down that cause a spectrum. So when light interacts with matter, matter has these quantized energy levels, and then the light is absorbed at a particular spot, and we call that a line. So lines and levels are totally different things. Lines are always differences in energy levels. So you can write that down. Lines are always differences between two energy levels. And you can see that over here. Notice how when you have a short arrow, this top arrow here is pretty short. Okay, that means the energy difference between these two energy levels is small because you have a short arrow. That means you have a long wavelength. So you have a low energy difference, a low frequency, and a long wavelength. Those three things go together for this particular transition. Now look at the longest one from E3 down to E1, this really long arrow right here. So that arrow right there, look how short the wavelength is. You see that? How high frequency it is. So you have a short wavelength, a high frequency, and a high energy difference between the energy levels. So if you'll just understand this slide, a lot of this course is buried on this slide. It's just getting your mind around a big difference between energy levels means a really short wavelength, a really high frequency, huge energy difference. A little tiny energy difference, that means a really long wavelength and really low frequency. Okay. Now, if those arrows were going up, this would be absorption. the system's absorbing light, but if they're dropping down, that's emission. Light's coming out of the system. And so if we scan our spectrometer and we look at a wavelength and measure how much signal, and then we go to the next wavelength and measure the signal and so on, and we're looking at a hot object, then we get a blackbody spectrum. And so this is the blackbody spectrum here. This is the wavelength in microns, so 10 to the minus 6 meters. And so way out in the, at 3 microns, that's the infrared region. So we're measuring the light intensity as we get shorter and shorter wavelength, and you see it's going up and up and up, and then it turns around and comes back down. So this is the emission spectrum of a blackbody radiator. We talked about the Rayleigh-Jeans law and the UV catastrophe last time, and blackbody radiation and the Planck distribution. And this is a function of temperature. We see 3 different temperatures here. Now you experience this every day in your house and even in here in this room, okay? Notice how the lights against the wall are a little different color than the lights straight above you. Look here. If you go to the store and you buy light bulbs, they talk about color temperature, a certain Kelvin. And you have here on the left 27 Kelvin, 2700 Kelvin, which is, or here's 1000 Kelvin, very red light. And then way up here at 10,000 Kelvin, a blue light, and right in the middle a pretty white light. So here's 5,000 Kelvin. It's white with a tinge of yellow. And look at our blackbody radiation curve here. Notice how we have all of the wavelengths, but it's a maximum in the yellow, and we have a little bit more red than we have blue. And so when you see these color temperatures on your light bulbs, they're telling you the blackbody curve that it's trying to match. Isn't that cool? So you've been dealing with blackbody radiation and you didn't really know it. It's the radiation that comes off of hot objects. And so if you have a light bulb with a hot tungsten filament, it gives off the light associated with these different temperatures. Now, how do we get the really high temperature light? We have to pressurize that filament with like a halogen gas, and that creates a much hotter filament and a much brighter white light. And that's where we end up with these halogen lamps being so hot. We've kind of gotten rid of them because they're fire hazards, especially the ceiling facing lamps. We would always have these Springer moths land on them, and then the moth would actually like char in the light, and it would stink, and it would make me like almost throw up. So my wife's like, stop, it's not that bad. But it was bad. So I'm glad we don't have those anymore. Now LEDs, they're trying to match these different color profiles. LEDs are light emitting diodes, and they give off individual like narrow spectral lines. And so they don't quite look right to your body. And so you'll notice somewhat different kinds of light from LED light bulbs. And it's because your brain, I guess, is expecting a blackbody curve, and it's not, right? And so something's not right. So even though you can't tell why, it just doesn't seem right. So this dashed line is the Planck distribution. But again, it's really difficult to think about this solid object with all of the atoms in that solid moving, and the equations for all of those electrons and all those particles are going to be too much for us. So I thought maybe I could model this blackbody curve with just a single electron on a wire. So just one electron on a tiny wire with quantized states. Now I've got to really crank up the temperature. Instead of 5,000 Kelvin, I have to go to 500,000 Kelvin because I've only got one electron. I might have like a quadrillion or maybe a mole of these little wires where all the different electrons have different energies. But I've got to heat them up to get an equilibrium distribution to give me that whole curve. Okay, so let's say I have a mole of electrons on a mole of little wires, and I have a temperature distribution of 500,000 Kelvin, and then I get this same kind of curve. So that's pretty cool. I have a few little humps down here, so it looks like I have 3 peaks here, but there's almost 50 peaks underneath this curve. And so what we're doing is we're simulating this blackbody curve with a particle in a box, that electron on a wire. And if you can simulate it, you have to know all the math that you put into the simulation. So that's what a lot of times P-chemists do. We'll go into it and say, well, if I can simulate it, I can understand it. And so we've simulated this black body curve with the particle in a box spectrum. And so now we'll take that particle in a box spectrum apart to look at the math underneath it. Okay. And so here's all the different kinds of spectral transitions we can have. This is from chapter 2. If you download that chapter from Blackboard, you can read about this. But these are all the different, just in terms of vocabulary. This is a nice vocabulary page. This first one is absorption. It's down there in the text, but I just want you to see. The photon of light comes in, hits a little particle, we'll say it's our electron, and now that electron jumps up to a higher level. And notice the light's gone. So you kind of read this left to right in terms of time. On the left, you have light, and then you have the absorption, and the arrow jumps up, and then we're done. It's absorbed that light, and the electron's now up here in an excited state. But that's not all that can happen. Let's do this one here. This is spontaneous emission. This is a U, not an N. It looks like an N. Spontaneous emission, where this electron up here in the excited state, all of a sudden, without provocation, spits out a photon. Well, it can't just give you energy. Something has to happen. It drops to a lower energy level. And that photon will tell you the energy difference between those levels. So this is spontaneous emission. And to this day, we still don't know what causes it. So this quantum jumping really frustrated Schrodinger. In fact, he wrote to a friend of his, he said, if we can't get rid of all of this damn quantum jumping, I'd be sorry I ever got involved in this enterprise. Because we have no cause and effect here. Now, a lot of philosophical chemists and physicists will say then there is no cause and effect. Just because we don't know the cause doesn't exist. But that's not required. That's a philosophical stance. So just because we don't know the cause does not mean there is no cause. But we still, to this day, do not know what causes a particular electron or atom to jump down and spit out a photon. If we knew it, we could control it. And this is a real issue for quantum computing. Like, we can use these quantum states as ones and zeros in computers, but we have to really cool them down so that we can slow down the spontaneous emission. So, now we can have stimulated emission, and this is kind of interesting. So this is stimulated emission because you have I'm just using the analogy of an electron on our wire. And along comes a photon, and the frequency of this photon matches this, or the energy of this photon matches the energy difference here. And when it interacts with that electron, the electron says, okay, and it drops down. Instead of absorbing that light, it drops down and gives off a second photon. And so now we have one photon coming in and two photons coming out. And so it's amplified. So this is kind of a neat process. This is light amplification. Go ahead and write this down because you'll like it when you get to the end. Light amplification by stimulated emission of radiation. And you see those first letters? That's a laser. That's what laser stands for. So this second process is a laser process. So when a photon comes in and you have a population inversion, you got more particles in the excited state than the ground state, then you get amplification and more light comes out than you put in. And then you put mirrors on both ends and it goes back and forth and it builds up 1,000 or billion, quadrillion photons of light, and they all come out at the same phase. So they're all together. Then we have scattering. Notice how we have a photon in and a photon out over all three of these. So photon in and out, if they're the same frequency, notice how the arrows are the same length. That's Rayleigh scattering. And then if the photon comes in, oscillates with the particle, but the particle comes down to a higher state, then it's going to scatter off a photon with less energy. And so that's called Stokes scattering, Stokes-Raman. So different people's names of these processes. Raman is a name, Stokes is a name. And then again, if you have a particle that's excited already and a photon comes in and interacts with that particle, it can interact with the particle, and then a particle can drop down and scatter off a photon of light with higher energy. And so that's anti-Stokes. And this is pretty much it for spectroscopy. You have absorptions, emissions, scattering, spontaneous and stimulated emission. So this is how light interacts with matter. There may be some other unknown processes to me, but this covers everything. It's going to cover 99%, and I can't think of the other one. Okay, so if you understand these 6 processes, then you can understand spectroscopy. Pretty sweet. Okay. So this transition, these jumps, these spectral lines, will give you, let's talk about absorption now, will give you a peak in the spectrum. So it'll absorb light and it'll be wavelength dependent. And so let's look at this equation, this absorption. So A for absorption here. Notice it's a transition between quantum numbers. It's temperature dependent. It's got a certain uncertainty about it. So this is your spectrometer, like how, what's the resolution on your spectrometer? And it's a function of wavelength. So it has all of these different parts in your absorption spectrum. Now the parts here, it's the sum of a bunch of individual transitions. And I've made, I guess, trying to come up with something that's memorable. You know, I like the phrase, go big or go home, right? And we don't want a tiny little peak, we want a big peak. And so the absorption depends upon 3 functions, BIG, Boltzmann, an integral, and a Gaussian function. So we're going to talk about those individually. Notice the Boltzmann function has a quantum number dependence and a temperature dependence. This I here doesn't have anything to do with temperature. It has everything to do with the 2 different quantum states that we have. And then this G here is the thing that's a function of wavelength. It has certain transitions, and it has this spectrometer dependent uncertainty. And so this absorption is dependent upon B, I, and G. So let's look at what B, I, and G are. So here's the spectrum that we had earlier. This is the simulated spectrum. This A term right here is this peak. And notice all of the pieces that go into that overall peak. So notice A is the sum, right? So the sum here, if we look at this maximum, that is the sum of all of these pieces here. This plus this plus this plus that plus that plus that, that. So all of those pieces added together at that wavelength add up to this point right here. Do you see? So sometimes when you get a spectrum, you see a big old peak. The top of that peak, it's not just one transition. It's the sum of a whole bunch of pieces of transitions. Now there's one transition that is right at that wavelength, but we're catching the side of this one. And we're catching this, a smaller part of this one. See, it still has some intensity down here. And then we're catching a lot of this one right there. And we're catching a lot of this one right here. So this delta L, or delta lambda, that uncertainty, the width of that peak, means when we're sitting at that wavelength for the spectrometer, we could be catching this transition for that electron on that wire, and this transition for that electron on that wire. And so if we've got a mole of electrons on a mole of wires, we get a whole bunch of different possibilities for transitions at that wavelength. And so we have a lot of absorption there. If we're way over here, it's still a sum of all these transitions, but look, the probability of exciting all those transitions is essentially 0 here. So even though we have 200 or a mole of electrons on a mole of wires, at that wavelength of 750 nanometers, none of them are excitable. And so our intensity is low there. So even though it's still a sum even over there, but there's just nothing, no intensity to add. Okay, so that's the sum part. Let's look at the Boltzmann distribution. So remember that these are transitions between energy levels. And so we have an energy level here, there, and we need to have molecules in those energy levels before it can absorb. And so this Boltzmann distribution is how probable. It's like statistics. What's the statistics that you're in the ground state? What's the statistics that you're in the excited state? And then the next excited state, and the next, and the next. So he's looking at the temperature dependence of the population of those energy levels. And if you're way high in energy, you probably don't have a lot of chance of being in that energy level unless you raise the temperature. If you raise the temperature, then you're going to put more molecules in those higher states. But the bottom line is, as the energy levels get higher and higher, there's just less of a chance that an electron is going to be thermally populated to that high energy level. So look what we see with the Boltzmann distribution. We see it drop off. As wavelength gets shorter, energy gets higher, and we see a drop off. And so this drop off here is how Planck solved that Blackbody radiation curve going to zero as wavelength goes to zero. It's because of the Boltzmann distribution. So he used that Boltzmann distribution of discrete energy levels to solve the blackbody problem. And here we see that dashed line, that's the Boltzmann distribution of those populations. And so even though we have lots of peaks up here, they're just a really small signal because of the B factor, the Boltzmann factor. And it's just tiny, tiny, tiny. So we might have a really strong probability of a transition, but there's just no molecules there, or electrons. Okay, and so then the I piece, we're going to unpack that in a second. But this I piece, so we draw this down to the Boltzmann there. The I piece are all of these little vertical lines. So this I piece right here, this is just a single value, and it's the height of the peak. And then this Gaussian is the peak shape. So it's this right here. And it has a certain delta L. So the certain uncertainty about this wavelength position, it's centered at lambda, say 1 to 2, and it's a function of wavelength on the x-axis. And so every one of these transitions is this Gaussian curve multiplied by this integral result, this I piece, the intensity, if you will. And then that's scaled by the Boltzmann factor. And then we add all of those together to get our overall absorption spectrum. So do you see the three pieces? BIG. B is the temperature dependence, the Boltzmann distribution. I is some sort of intensity factor. We'll figure out what that is in a second. And then G is the shape of the curve. Okay. So let's take each of these pieces and look at them in detail. Now, this I piece is going to involve integrals. And so let's take a pause here and talk about Dirac notation. Normally, in calculus, you were dealing with integrals, and here's a particular integral. We have three functions times each other. We have a wave function here multiplied by the x-axis multiplied by another wave function. And this little star here means the complex conjugate. Okay, what does that mean? Well, if you have, let's just say y equals a plus ib, right? So some imaginary number, then y star is equal to a minus ib. So the only sign that changes is the I. Notice a is still positive. So the complex conjugate, wherever there's an I, you change the sign. We only have to do this in one of our wave functions, okay? But anyway, it's for the particle on a ring in our class. But anyway, that's what we mean by that complex conjugate. The nice thing is then if you multiply these by each other, then you have the IB and the minus IB cancel each other out, okay? And that's nice. Now, we got tired of writing, the integral of this business dx, and so Dirac got lazy, and he did this shorthand. And so that's what these brackets mean. So these brackets here and these vertical lines just means times. Okay. Okay. And these brackets mean the integral. Over? What language is that? Over all space. So instead of over, I put over. So, yeah, let's see if I can erase that. Yeah, I got an eraser. Okay, the integral over all space. And I spelled space with an S. That's crazy. What's going on with my brain? Check me for a stroke. Okay. At least they sound the same. Isn't that weird? Why does the brain do that? Okay, now overall space, that could be in XYZ, or it could be r theta phi if you're in a like an atomic coordinate system or spherical polars. But we're going to keep this simple and just do it in one dimension. So for our rules today and next week, it's just going to be over x. So the integral over x from minus infinity x to positive infinity x is the integral over all space. If we're in a box, it's just from the left side of the box to the right side of the box. And we want it centered on 0, so it'll be minus from minus L over 2 to L over 2, and that's all space for us. Okay. Now let's talk about this I factor in the middle, this transition moment integral. Now we have two different types of spectroscopy. We have the absorption emission spectroscopy and scattering. And so we have two different types of transition moments. This is the absorption emission one with this little A up here. And then this is all of the scattering. And notice the only difference is this in the middle, X. Okay. So this, for absorption and emission, we just have one photon. And you can think of it as plane polarized light. So we have our little electron somewhere on an x-axis. So it's got a wave function here on the x-axis. So that's our electron wave function. And we want light to interact with that. And so we're going to have plane polarized light in the x direction coming in here, interacting with that electron wave function. There's only one axis, and so we can really only have one photon electric field. And where's that electric field going to be? It's going to be on the x-axis. Now, think about light being an electromagnetic wave. It's going up and down in its electricity, and it's right and left in its magnetism, so electromagnetic. And the electric field is about 1,000 times more potent than the magnetic field. And so we're going to interact with the electric field of light. And so on our x-axis with our electron, on our little antenna, light's going to come in along that antenna. And so we're just going to use the x-axis to behave like light. So we could put in there the permittivity, the vacuum, and the electric field strength and so on, but those are all constants. So we're just going to use x and scrub out all those other constants because we're looking at relative intensities. We're not trying to calculate the absolute intensity. So relative intensities are good enough for us. And so light's coming in on the x-axis, interacting with our electron on that little wire. So my finger's a wire, and light's coming in here, and it's going to interact with that. So that's one photon of light coming in, interacting, being absorbed. Or my electron's in excited state and it emits. Well, how's it going to emit light? It's on an antenna. The light's going to come off that antenna in the x-axis. So we still just have one photon, either absorbed or emitted. But scattering, light comes in, interacts with the particle, and then leaves. So we have two photons. And so that's why we have x squared. Simplest explanation. We could talk about polarizability and how the electron cloud polarizes, but that's a simple explanation is to say it's two photons. So we have two of these X operators. So notice how scattering is x squared in the middle, and absorption emission is just 1x in the middle. Now these psi's, those are wave functions. So here we see our first wave function. So we have absorption was big, Boltzmann distribution, this integral, which we're looking at right now, and Gaussian, and the integral here has the wave function in it. So it's depending upon the wave function. We don't know what that is yet, but we're going to look at that in a second. So we're drilling down. Right when we get to intensity, we realize the intensity depends upon the wave function. Here's the Boltzmann distribution. So some energy levels have degeneracy. Remember your like 2s and 2p energy levels, the 2p orbitals were same energy. So this would be, for G would be 1 and 3, right? There'd be a degeneracy of 3 for the p orbitals, and for the d orbitals 5. So that's what we mean by degeneracy. How many orbitals have the same energy? Now in our particle in a box, we don't have any degeneracy, but it's in the Boltzmann distribution. So it would just be 1 for our system. Then it's exponential dependence upon the energy of the electrons here, this energy term, divided by kT. So this is Boltzmann's constant. And the temperature. In Kelvin. Okay. So it's kind of interesting. It's looking at the temperature of the system in Kelvin. It's scaling that by Boltzmann's constant, which is like 1.38 times 10 to the negative 23. Thank you. Joules per Kelvin. So look at that. If it's multiplied by T in Kelvin, then we get out of Kelvin and into joules. So it's a way to convert temperature into energy. It's like how many joules do you get for every degree of Kelvin? So that's what Boltzmann's distribution is calculating. And then it's looking at the energy levels of the system. So we have these different energy levels. And so we might have them labeled 1, 2, 3, and 4. And it's saying for energy level 1 compared to the kT, how much, what's the statistical probability that I have molecules in energy level 1? And then energy level 2 is higher, divided by this kT. It's going to be e to the minus x. It's going to be a smaller exponent. Let's see. No, it's going to be a bigger exponent because we have a higher energy. And since it's negative exponent, it's going to be a smaller factor. And so the probability goes down as I get higher and higher in energy. So what we end up seeing is a lot of particles in the lower state, fewer particles there, and it falls off exponentially. So that's the Boltzmann distribution. And notice that where do these energies come from? So we have to figure that out. All right. So Boltzmann depends upon the energy levels. The intensity depends upon the wave functions and light. And the energies come from the Schrodinger equation. So here's the energy equation. And this is just a different form of the Schrodinger equation, but it is the Schrodinger equation. And this H piece here is the Hamiltonian. Or the total energy operator. So how does this look? Well, we have this Hamiltonian in here, and it's multiplied by the wave function. But it's not a simple multiplication. We call it operating on. It's an operator, because look what it has in it. It has this second derivative operator. So it's not just times the wave function. It's actually doing something to the wave function. And then we have this V. This is the potential energy here. So this first piece is the kinetic energy, and the second piece is the potential energy. And so we're getting all of the energies of these systems. Now, potential energy for these tiny little systems would be attraction and repulsion of nuclei and electrons and so on. But what we have, we're just making a very simple model. We put an electron on a wire, and we've zeroed out the potential energy. So we're saying there's no difference with the edge of the wire, or the middle of the wire, or anything like that. Is it realistic? Not exactly, but it's close. Okay. Even a molecule, like you might have, acetylene with the carbon triple bond, you could treat those pi electrons on that molecule like a particle in a box, because they're stuck on those two carbons. Yeah. Okay, so we have this energy equation, and from this we get the energies. Okay. And so then it also depends upon the wave function. So the intensity depends upon the wave function, the energies depend upon the wave function. And so here's our wave function. It's a sine function, and so you're familiar with the sine wave. Okay. So it goes from 0 to 2 pi, like this. But what we want to do is we want to take that and we want to scale it. So right here's 1 pi in the middle. And we would like this maximum x to be pi, right? So how do we make that? Well, we say when x is divided by L, it goes from 0 to L. So if we have x over L, that allows us to go from 0, and when x is equal to L, then this ratio is 1, and it's 1 times pi. So putting x over L scales this to where now this is 0 to L. Okay. And then when we have this in here, this is our quantum number. If that goes to 2, then this looks like it goes from x going from 0 to L means that we go from 0 to 2 pi. And then if it's this 3, then we go from 0 to 3 pi. And so as we change our quantum number, this is n equals 1, this is n equals 2, this is n equals 3. And if we plot these 0 to L, then we have our 3 little wave functions. But I'd really like this thing to be centered on 0, because we're going to do symmetry later, and we're going to look at these functions and determine if they're even or odd functions. And it's nice if everything's symmetric around 0. And so I'm just going to shift this 1/2 of a wave to the left, and that's what this piece does. Okay, so this shifts it so that our quantum numbers, our wave functions look like this. So minus L over 2 to L over 2, and we have n equals 1, and then this would be n equals 2, where it goes through the 0 like that, and so on and so forth. Now I've got them plotted on the next screen. So here's our first 3 wave functions. Now these are standing waves, very similar to what you would imagine a guitar string. So you pluck it and it's oscillating up and down, or it might even be like spinning, like going forward and backwards too. But in our situation, we only have one axis. We don't have a z-axis or an x-axis. So this, how do we even understand this? Well, it's a wave that describes the particle, and it's oscillating between its real and imaginary parts. And so it's like spinning in and out of the real plane and into and out of the imaginary plane. And so it's conceptually very similar to a guitar string. Okay. But there are no other axes, right? There's no x-axis, there's no y-axis. I mean, there is an x-axis, there's no y or z. And so where is the wave, right? Like, if there's no y-axis and no z-axis, then what is being off of the x-axis mean, okay? And so these are concepts that just burn your brain, okay? And if it's burning your brain, that's fine. That's mine too, okay? We're just describing this particle with a wave, and it's going to match our experimental spectrum. So asking some of these questions that you want to ask, like, what does it mean when this is plotted over, off the x-axis? What's there? There's nothing there. It's just a plot of the function. Okay. Now, also, this is strange that this wave is oscillating. Is it real or not? This is also a philosophical question that we can't answer. Okay, we're describing all of matter with waves, but what are those waves and why they don't ever decay? Why don't they stop? What's keeping them going? Right? Have you ever thought of that? You pluck a guitar string and eventually it just, it stops vibrating. Okay, but these waves don't ever stop. What started them? What stopped them? These are philosophical questions that we can't answer at this point. I mean, there are answers. There are philosophical answers, religious answers, and so on that people have supplied, but it's really hard to answer those questions empirically because there's no way to get our fingers on those waves that are not in any of our coordinate systems. Okay, like in this example, we just have the x-axis. That's it. Okay, so this is where the weirdness of quantum mechanics comes in. If you start to ask, what is the wave function really? Then there's whole books written about that. Okay, I've read a few of them, so if you're interested in that, we can talk. All right, but as far as we're talking about the wave function, this region where it's oscillating is called a lobe, like your earlobe, okay? And the place where it's not is called a node. And so I've labeled a couple of those on here. I've labeled the lobe and the node. But now you can also kind of see the symmetry, right? This has a mirror image, left and right. This has the opposite image, left and right. This has the mirror image left and right. You see those symmetries? Okay, good. So that's going to be important in the next part of the course. So let's just recap. We've got these energy levels now. These wave functions have been plotted on a different axis, on an energy axis, and then their amplitude has been multiplied by 200 times, just so that you can see that they change. So these are the energies of these levels. For an electron on a 7 angstrom wire, there's quite a big difference in energy. And so we can have transitions between these different levels, right? So this electron down here could absorb light and jump to those other levels, or we could have emission coming down. And so those would be called transitions. And so the transition equations are all the differences in these energy levels. So in N prime is the higher level or lower level, it doesn't matter, like initial and final levels. And so we have a delta, these differences in energies gives us delta E. And so then E equals h nu. So we can rearrange this to the frequency. That's the Greek character nu. And this is wavelength. Lambda. We'll change that to a B. Okay. And so these would be the transitions. This is the locations of those peaks. So this right here, let's focus on this one since our spectrum was plotted by wavelength. And so now we have those lambda 1 to 2. So this is the energy difference, or the wavelength for the transition from energy level 1 to 2. So now we know exactly what that peak is. That's that ground state to the first excited state absorption occurs right there and nowhere else, because that's the difference between those energy levels. And then the next one, going from 2 to 3, is right here. So notice if we can simulate it, we know what goes into it. We can explain it. And since we simulated this, we know exactly what that peak is. That is the electron in the ground state going to the excited state on a particular wire. And then this is a different electron on a different system. It's in the second excited state, and it's going to third excited state. Or I changed those words. It's from the second quantum state. It's the first excited state. So the second quantum state going to the third quantum state is right here. And then what do you think this one is? This one is from 3 to 4. So n equals 3 going to n equals 4, n equals 4 going to n equals 5, and so on. And all of these things depend upon the energy, which comes from the wave function. The intensity comes from the wave function. Here's the wave function. So if we can understand the wave function for the particle, whether it be a molecule, an atom, an electron, we can understand everything about its spectroscopy. That same wave function will tell us all of the properties of its chemistry too, because it will tell us where the electrons are. And that's one of the postulates of quantum mechanics, that the square of the wave function is the probability distribution for that electron or that particle. So it will tell us where it is. Okay, and that's what we'll talk about next time. Okay, so we'll see you then.